Well, welcome to our first keynote. Apologies for the delay. As expected, we'll always have technical difficulties the first day. So our first keynote is from Professor Hrvoje Jasak. He has a very impressive bio. Hi, Hrv. Nice to see you. I suggest everybody reads it on the right-hand side. It's I think you can probably write a book on your bio, Hrv. So I met Hrv first I think it was in Penn State. As a naive PhD student, I think I wandered up to you after your keynote then, and I think you gave me some good advice at the time.
Hey, Phil, are you back?
I'm back. Sorry, I got kicked off there. So I'm not sure if you got the end of it, but I'm looking forward to your talk. So if you want to leave some time at the end, I think we're scheduled until 5 to. So if you can stop short of 10 to, it will give us some time to answer the many questions.
Thank you very much. If you let me share the screen, I can start.
Sure. Are you able to share yet?
That's right. Okay.
Great.
You are, and you can hear me, Phil, right?
Yeah, perfect.
So thank you, everybody. Thank you for coming. Thank you, Philip, for showing us the movie of all the wonderful places that we cannot visit in Ireland this time. I'm definitely coming to visit sometime soon. It is my pleasure to be here on the 16th OpenFOAM Workshop. And as you've heard, Zagreb was mentioned a couple of times. But now everything is done much more seriously and much more nicely. So I will start by saying a few words about OpenFOAM in the year 2020. You know that this is the second OpenFOAM workshop that was killed or rescheduled by COVID, but this time Philip made a wise decision to do that earlier. There is quite substantial news to talk about, and I always like showing some nice presentations. I have already seen two of them stealing my thunder, which is really nice to see because usually I steal the nicest presentation slides from other people and show them in the keynote before everyone else. So thank you. I will point out who the people are. So to start, thank you for the organizing committee. And here you can see the list of some friends, old friends, and very, very old friends. So as Philip said, he's in the category of old friends. I know Neil Murphy longer than I know Philip, so we'll call him a very old friend. And Professor Alois Ivankovic is definitely my very, very, very old friend. But let's not pick on him because he might speak back. On the right-hand side, I was really happy to see this logo made out of made-free additive manufacturing. But then I realized that it says iForm rather than OpenFOAM. But hopefully we will be able to deal with that. The virtual event in 2021 is a huge amount of effort as usual, and I'm really grateful for everyone who has put in the work to make this event happen. I have been talking to a bunch of people over the last year, and I always start with the same question: are you safe and well? How are you coping? And to this, I will add the question of, has COVID made you take up some strange hobbies? And here's a little movie of a strange hobby. Just as a comment, this qualifies as experimental work, and I don't do experiments, so it's not, in fact, it is not me. But what you can see here is the game of skipping stones, which brings us to the first showcase that I would like to show, which is a numerical study of skipping stones at the University of Cambridge. It's done as a part of the master project by Stefan Nixon under the supervision of Professor Stuart Deer. And the software is being used is the Naval Hydro Pack with all the bits that we have. And I think it's fair to mention one of the sponsors, which is Pointwise, which in the meantime has become Cadence. So what we are doing here is we are wading into the arguments of what can happen when you're trying to skip the stone. And what you can see here is a 6 degree of freedom stone moving, hitting the free surface and then pitching up. And 6-year-old Hrvoje used to think that this is how you skip the stones. But in fact, it is more complicated than that. There has been a big discussion about whether you can do that without rotating the stone around the vertical axis. So if you add vertical axis rotation around it, then the stone will jump off differently because the rotation around the vertical axis gives it gyroscopic stability. You can also see that these are preliminary simulations, so our free surface gets messed up a little bit before the impact, but now you can see nicely how the stone turns. Interestingly, this is a subject of some concern, meaning that doing experiments is not easy. And in fact, a set of experiments has used a rate of rotation of about 100 radians per second, which is faster than I can throw the stone. So at the top of the picture, you can see my omega rotation tensor. The stone is an oblate ellipsoid. It is assumed that it's got a simple surface. It will hit at a certain pitch angle. On the left-hand side, you have the roll and pitch in case there is no vertical rotation. And you can see that the stone pitches up, which makes it unlikely that it will skip again. Whereas with the vertical rotation, the pitch angle is smaller, and then everything seems to be behaving nicely. What I like about this is that doing experiments with skipping stones is not as easy as one would imagine. And with CFD, we can quite accurately model what is going on. And because of the experience that we have in the simulation of free surface flows, we can actually put error bars on the simulation and carry on with that. This project has kept me amused through the winter, and I hope in the summer that I can join Stuart and doing some experiments myself. So what are the other news? So for me, the most exciting news is the OpenFOAM governance. The committee activities are wrapping up. We are meeting. You can check that on openfoam.com. Governance, Dr. Fred Mendonça of ESI OpenCFD will speak about that in his keynote. And I would like to put to the spot Professor Gavin Tabor from University of Exeter, who is coordinating us and making sure that we can do things. There is a list of technical committees, but currently we are also building up application area committees, which will involve things like external aerodynamics, as well as the ones that are written down. And we are seeking members of contributors. So please join us if you can, because in this way, we can make OpenFOAM even more useful, not to mention user-friendly. The second big piece of news is that we have a substantial project under the Euro HPC call of 2019 with the idea to prepare foam to actually run properly on exascale platforms. So we need to address the OpenFOAM technology for industrial users as a priority, and that brings the same capability to the rest of us to get extreme performance on the HPC platform. That involves novel algorithms, rewrite of some of the stuff that may be limiting our efficiency and scalability, refactoring, porting, and seeking other sources of performance. The objective of the project is to deliver working simulation software. So we are not just playing, we are actually using the software to deliver the exascale solution. For more information, see the ExaFoam website, where there is a few slides on what the project does, how it is structured, and what we expect to see from it. Moving on to some more interesting news, that was an itch that I had for quite a long time. And it is about rapid prototyping. So Hrvoje and I had arguments about ideal matrix formats for high performance computing, but working with that within the OpenFOAM structure is not easy. If you want to change the matrix storage structure, you're working with 1.5 million lines of code. It compiles for a very long time. It does all kinds of things. It is hard to use in teaching, and rewriting the CPU intensive or computation intensive parts of the code is hard. So Robert Anderluch from the University of Cambridge has worked with me, or I told him what to do, in order to implement a lightweight finite volume simulation framework, which looks like OpenFOAM, but it is written in Python. The reason why to write it in Python is that debugging is easier. We lose a lot of luggage like virtual base classes and runtime selection tables, and we can re-implement the bits of the code which are performance specific to find out who can propose a better HPC framework that can be rolled out within the more demanding C++ structure. All of the dictionary data, input, output, and in fact, everything apart from the mesh has also been moved into Python, which means that Bernhard Schneider and his approach finally win. The kind of functionality that we have is polyhedral mesh support, second order finite volume method, linear equation solvers, and 3 top-level solvers, Laplacian foam, icofoam, and SimpleFOAM, which allow us to run, I don't know, a motorbike tutorial or some serious external aerodynamics cases and find out how the code behaves. So what do we get? We are working with a small package. The whole of foam Python is several thousands of lines of code rather than 1.5 million. We can quickly experiment with the basics. And here I don't mean implementing new turbulence models. I mean changing the way that the solver assembles and solves the matrices, and find out what things we can do in order to adapt to the new high-performance computing platform. So here is a little piece of code. So you will see that this is not a copy of what OpenFOAM looks like, but actually creates a matrix for the DDT, Laplacian, sums them up, and then calls a solve. All of this is in Python. And Robert will do a presentation later on to show you how this is made fast, efficient, and useful using things like NumPy and CPython. Moving on, I have to say that I have already seen an excellent presentation this morning on batteries and fuel cells, which proves my first point. And that is that OpenFOAM can do multiphysics simulations really well. Anything that can be described with continuum equations, with the possibility of zooming in into porous reaction zone or microstructures, or implementing surface reaction, fits within the concept really well. In the past, we have done work on fuel cells, but I have been obsessed with batteries for a while. And having done some work on lithium-ion batteries, a new type of battery has really grabbed my attention. And this is, of course, the lithium liquid metal battery. It started with a presentation from Professor Sadoway from MIT saying that lithium-ion batteries are not appropriate if you need power. And the kind of power that I'm talking about is the renewable energy capacity of the Great Britain network, which can harvest the wind and, I don't know, tidal energy, and then needs to store it. We need to have high power capability that will use cheap materials, simple design, and it will not deteriorate over the large number of cycles. And an example of one of those is here on the picture on the left-hand side. So my ideal battery would be liquid, 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 but in this one, bismuth at the bottom is liquid. Then we have electrolyte, which is also liquid. And finally, to simplify our system, the cathodic lithium electrolyte electrode is actually made as a spongy solid rather than a liquid. You will pack this in in about 60 cells per tray, and then stick 10 trays into something of the size of a shipping container in order to create large storage capacity. Being able to do that is really nice, but it involves problem with free surface stability. So the instability will occur because batteries talk to each other through magnetic fields and upsetting the surface between my bismuth liquid at the bottom and dark blue solid lithium can cause the battery to short circuit. What you can see here is a little piece of simulation from Fedor Misura, again from University of Cambridge, looking at how the thickness of my electrolyte changes and finding conclusions on how to package the components of the batteries together in order to get the performance. I'm really looking forward to some collaborative work on this subject because I think liquid metal batteries are really coming and they're going to be as important as internal combustion engines have been in the past. Moving on to another thunder of mine that has been stolen. Luca Balatinec has just presented the work on lubricated contact, where we can calculate the mixed mode sliding contact between two moving surfaces, including lubrication, elastic and plastic deformation, cavitation, and various other phenomena. And in fact, we can use a measure surface roughness from the two surfaces to get predictive simulations of what's going on within the contact. The work has been done in collaboration with Afton Chemical, and it was one of those, well, this is a great job, it's really fantastic, but we're interested in something else. So it turns out that the point of interest in these simulations is not the lubrication state, it is the wear rate. So building up on the model from Luca, we are working towards a wear model, which will include information on how the surface profilometry changes during wear and how that redistributes the load and influence future wear rate. A few pictures here. So this is our simplified simulation using a dry contact of a pin, that's the little vertical cylinder here, with a rotating disc, where we can calculate the contact pressure, elastic deformation, and then follow the wear depth on the rotating cylinder underneath our pin. The work is ongoing, and there is quite a few things that we are going to do here, starting with implementation of more sophisticated cavitation models for lubrication simulation. That will be presented by Fran Delic, and other phenomena that are really involved in this kind of simulation. Moving on, I would like to show you a couple of simulations that come out of University of Zagreb, and they are both master students. So the first one was involved with kinetic turbines harvesting ocean current energy. Okay, you can see what they look like, but putting these things in the ocean is not quite as easy as it is. You will appreciate that with wind turbines, you have a significant wake behind them. But in water turbines, the density of the water is 1,000 times bigger. So the energy in the wake is also going to be substantial. The usual question of how do we optimize local relative position of one kinetic turbine towards the other is still there. But we also need to look at the effects of seabed scour. Okay, so here's a little movie showing you how seabed scour develops in such a simulation. And what you can see here is quite a complicated solver because we are using multiple rotating reference frames, i.e. turbo machinery features, to capture the rotation of the turbines. There is a free surface on the top of this animal, and we are looking at the scour profiles for various formations of these turbines relative to each other. The work has been done as a master project with Anna Lisats at the University of Zagreb. The second sort of connecting project relates to turbo machinery simulations. As you know, the features that we need to do turbo machinery well are numerous and they're really quite sensitive and complicated. So GGI, AMI interfaces, partial overlap, partial cyclics, mixing planes, moving mesh, multiple rotating reference frames, rotality with jump conditions, etc., for incompressible and compressible flows have been implemented for a while. And quite regularly, I get questions, well, why doesn't this work for me, etc. And it turns out that this code is used all the time. So in fact, I know that it works. And as an example here, I'm going to show you a flow, a compressible flow in a centrifugal turbo compressor done as a master project of Matej Chorak. So what you can see here is various features of the flow velocity in the middle, enthalpy variation, including the rotality jump condition. And on the picture on the right-hand side, you can see that the inlet plane flow is not as simple as one would imagine. As I said, there are lots of features and they are not easy to use. So you may need help or training. And the ideal place for that is the Turbo Machinery Working Group. It used to be a very successful and very active group. And recently, through the efforts of Håkan Nilsson and Martin Badoan, it has been revived. There will be new features, new tutorial cases, and new validation cases. So please reach out to Håkan and Martin to join the game, because we are at the position where OpenFOAM can do turbo machinery pretty well. Stronger together. What do I mean with that? Well, in order to create a good simulation code, we need to be able to collaborate with each other and push towards the features that really not only implement new CFD methodology or new physical models, but get them to work in a robust and reliable manner. So how do you do that? Well, first, try and write good code. Use good programming practices, understand physical models, consider the efficiency, provide I/O, HPC, ease of setup, which is something that OpenFOAM is not famous. But the second one is get a lot of people to use your code on a regular basis, find out what doesn't work, and fix it. And that means you. Having active, engaged, and contributing users who not only report successes, but report problems with the code is an excellent way of contributing to this project and making sure that OpenFOAM lives long in the future. I also have to tell you, nobody's time is free. We all eat and sleep. So don't expect that just by posting a question on the user forum or engaging with a special interest group, somebody will fix your problem for you. An important aspect of all this is education and training. Creating a capable and engaged community requires effort, okay? That starts by senior PhD students teaching junior PhD students what the code is like, how it works, running master projects, running seminars, commercial or free training sessions, writing books, videos, and tutorials. They are all very important aspects on that. We have our hero here, that's Joseph Nagy. I understand that the book, I think it's called the C++ Primer, has now been released in PDF free of charge. And finally, we have turbo machinery, turbulence, and aerodynamics special interest groups that will push the knowledge and the capability of the code further. A little bit of an advert for me. There is higher level training as well, where the point is to create software development and simulation specialists. Currently, we have the MPhil and PhD courses under my mentorship at the University of Cambridge. There is a whole network of research organizations worldwide. So whoever is presenting on this conference didn't just show up with nothing. There's substantial knowledge and experience with the code behind them. I used to run the NUMAP-FOAM summer school, but for the last 2 years, it has been eaten up by COVID. And there is also the High Performance Computing Academy being run at the University of Cambridge, which will teach you what kind of things you need to do in order to do HPC well. Incidentally, I'm hoping to restart the summer school in 2022, and you will be informed in the usual way. So on that note, let's all start pushing or carry on pushing in the same direction. And I would like to thank you for your contribution to OpenFOAM source code, OpenFOAM project, OpenFOAM activities, and this experience of speaking to you on this virtual conference in Dublin. Thank you, Philip.
That's great. Fantastic, Hrv. Thanks. I've no doubt many questions on ExaFOAM, but also on Python foam. Let me just check if anyone has any questions. Please put them in the Q&A. Hakan commented in the chat, and it's quite a long message, so I'll try to summarize it. Himself and Martin have been working on the Turbo Machinery working group for a while. It's work in progress, and he's suggesting people to please join him on Thursday to discuss, and he's posted a Zoom link. So this is this birds of a feather. I think you'll see a bird appear at the top of the main, above the timeline, so you can click on that and you can join him there. We don't have too much time ahead of the training is in 4 minutes, so maybe I'll ask you one question on Python foam, or I'm not sure if you have a name for it yet. Is it reusing any of the OpenFOAM code, or is it actually just rewriting everything? It's just rewriting everything.
Nothing.
Okay.
What my boss told me is you have to make your master's students write the code from scratch.
Okay.
So I said, well, what I want is a little one that looks like and feels like the big one. So we are reading in the mesh because that's the painful bit. And the mesh is being read straight from the OpenFOAM files. Mesh analysis is done completely within Python. All of the matrix assembly, matrix solution, fields, boundary conditions, etc., are also done in Python. And you can make it run fast by using either NumPy or CPython that I know little about. The
Sure.
output is again in the format that's compatible with OpenFOAM, so that we can use Kitware's product ParaView for post-processing. But it's really a little baby that's rolling there looking to be used in the optimal way, like, for example, rewriting numerics in the GPU adequate format.
Okay.
So hopefully more to come.
Fantastic. And do you plan to share that or make a public repository, or you will see how?
Robert will be doing a presentation during the teleconference. I have no rights or ownership over it. It's Robert's toy. I think it's public already, but
Great.
we will find a way to enhance it. It has got an important role within the ExaFOAM project, where we have to argue about matrix formats, HPC efficiency, etc. So I'm hoping that there will be dozens of people working on it by the end of the year.
Yeah, no doubt, given the user base of Python and how usable it is. I also would like to play with it from having pain of trying to link OpenFOAM with Python. It would be nice to just have it all in Python. So yeah, that's fantastic. Yeah, we've only a couple of minutes left of the training. So I'll just ask one last one on the ExaFOAM. Will that merge after that project finishes? Will output from that project merge back into public releases, or it will depend? That's the intention, is it?
Yes, every single line of the code being written will be open source, and it will end up in at least one and maybe multiple forks of OpenFOAM, with the idea of eventually providing one OpenFOAM, which is something that I kept on going on about for a year.
Great, fantastic. Okay, sorry to cut it short there, but I'll thank you again. And yeah, it's a pity we don't have an applause or an applause button, but I'm sure there's 177 people applauding at the moment. So there are some people maybe in the chat who might have some questions that you might have a look at. But that's fantastic. So thanks again.
Most definitely. Thank you, Philip, for putting the effort to organize all this.
Sure.
I'm honored to be your guest in Dublin.
Yeah, thanks very much. It'd be great to have everybody in person here in a few years' time. So we'll wait till things get easier. So fantastic. Okay, I'll see everybody in the training sessions, which will start in the next couple of minutes. So thanks again. Bye-bye.
Bye.